Welcome to Chemical Process Safety. This video will be about the second of the two inerting techniques. The last video covered cyclical techniques. This one is going to cover sweep-through purging technique. In sweep-through purging, it's continuous, so I'm not doing one step and then the other. I'm adding inert while at the same time I'm venting by relieving that stuff that I've added. I'll assume perfect mixing, constant temperature, and constant pressure. So this is nothing but an unsteady state material balance, which I like to cover. I don't know if you covered it in your material and energy balances course. But just to define some of our variables, we'll call the volumetric flow rate of inert Q sub V. We are not going to be adding volume. That would be impossible. So however much volume we add, we also must be removing. So that's why QV is the same both in and out. C0, I will call the composition of the inert material. So it could be 0% oxygen. That would be an idealized case, but it doesn't have to be. So we'll keep it general to account for the possibility that 100% pure inert is not going to be possible. Nor would it be required, right? As long as the concentration here is below the limiting oxygen concentration, that should be okay. And that varies depending on the fuel. But if this was 5%, say, once this gets to steady state, we'd have 5% oxygen inside the vessel. And again, that is going to be enough. So use the cheapest stuff that will get the job done is the other way to think about this. TP and volume are fixed, and anytime TP and volume are fixed, then that means the moles are going to be constant, and that's another reason why I could say the volumetric flow rate in is equal to the volumetric flow rate out. I've said that we're assuming perfect mixing, so C of T is the concentration of oxygen in the outlet, and by the well-mixed assumption, we can say that the concentration of oxygen in the outlet is equal to the concentration of oxygen in the vessel for all times. And that's just what this bullet point says. So the derivation for this equation starts with material balance. Here I've got accumulation, dm dt, is equal to input minus output. And I'm performing this balance on oxygen. I need to be careful to say. So I can factor out V because the vessel is going to be a fixed volume. And call it V times dc dt is equal to, now concentration times volumetric flow rate is equal to mass flow rate. So that's what I've done in this step. Also pay careful attention to C0 is the incoming, not the initial. Those are two different things. So C0 is what's coming in, times QV minus C is what's going out. So again, in minus out. This is a separable differential equation. So I can factor out a QV here, and then I can bring C0 minus C over to the other side. And then the volumetric flow rate and the volume are both constant, so I can pull those outside of the integral. I then integrate, so this has the form of 1 over A minus X. The integral of this left-hand side is minus ln of C0 minus C, and the integral of this side is simply QV over V times T. Can't forget about the plus the constant either. I then solve for C, or that's what I'm aiming to do. I do that by multiplying through by a negative and taking the exponent of the whole equation. And I always like to make this point in MEB that the constant that I have at this step is different than the constant that I have in that step, but I don't necessarily care because I haven't solved for it yet. I will solve for it in just a second, but I tend to avoid performing algebraic steps to my constant because I find that to be clearer. And then the next step is I solve for C. So I just take C over to the other side. I take this entire thing over to the left side, and I end up with this expression. And now I want to solve for what the constant is. So I need my initial condition. At time is equal to 0, the initial concentration of oxygen inside the vessel is 21% or whatever the C initial was. And that's just for regular air. So I kept that general here, but you can plug in 21% and you could obtain an expression as well. So something you can do here is calculate the time required to get down to a specific concentration. So again, if you are starting with pure air and you want to get down to the in-service oxygen concentration, that would be a general problem. For a specified flow rate, a specified volume, and a specified purity of the inert. You would plug those numbers in and you could solve for the time. Let's look at an example problem that will look at all situations. Calculate how many cycles it would take to reduce the oxygen concentration or content from 21% to 10% using nitrogen containing 9,000 ppm of oxygen. We'll look at three situations. One is using a vacuum with minus 200 millimeters mercury gauge pressure. Second one is using a pressure purge of 200 millimeters mercury pressure. And the third situation will be finding the time required to purge the vessel with sweep-through purging if I've got a volumetric flow rate of 2 meters cubed per minute and the vessel is 5 cubic meters. The situations are not completely analogous, by the way. So notice that for pressure and vacuum purge, I need the same variables, whereas with sweep-through purge, I need a different set of variables. So I'll pause the video now, or you should pause the video now and see if you can work out the answers to these on your own. For part A, the first step is to use the vacuum purging formula that we derived in the last video. So Yj is the final concentration of oxygen. Y0 is the initial concentration of oxygen. P low is going to be 560 millimeters of mercury. P high is going to be 760 millimeters of mercury. I could pick whatever pressure units I want, by the way, because there are no units, or the units are going to cancel. So the first thing I might want to do, just so that I have an easier way of using this equation, is by solving for J, or rearranging to solve for J. So here are my algebraic steps with that. First thing I did is I brought Y0 over to the other side, and then I took the ln of both sides. And then to isolate the J, all I have to do is divide through by ln of P high over P low. And I did this first because I'm going to copy this formula and I'm going to apply it to the pressure purge scenario as well. Okay, so next step is I'm going to plug in the numbers and solve for J. And when I plug those numbers into my calculator, I get 2.4. But for a cycle like this, I don't want to mess around with having a partial cycle, so always round up in these types of problems. So 3 cycles would be my final answer for the vacuum purge situation. Now for the pressure purge situation, it's going to be very similar. The only difference is, again, my pressures. So this is the pressure scenario. So ln of 0.1 over 0.21 divided by ln, and now it's plus 200 millimeters of mercury gauge. So it's 760 on the top and 960 on the bottom. So let me calculate that and we'll see what our answer is. And for pressure purge, I get 3.2, which I'll round up to 4. So once again, the main idea here is that pressure purging is going to be easier from a pump standpoint. It's going to take less time in order to pressurize the vessel, but the downside is it's going to require more cycles and more inert. So there's a trade-off at play here. All right, finally, let's do the sweep through situation. So I need to take this equation. So C is equal to C0. Oh, you know what? I messed up on parts A and B. I did it for 100% pure oxygen. I did not do it for 9,000 ppm of oxygen. So that was a mistake on my part. Since I wrote this problem, I might delete that from this part, but keep it in this part. You know what I'll do? I will, at the end, I'll go back and I'll do it again, but for 9,000 ppm, and then we can compare the answers. But let's keep going. Let's do part 3 first before we do that. So C is equal to C0. To keep in mind again, what is initial versus what is incoming. So what is incoming is going to be the 9,000 ppm. That is not, of course, a mole fraction, though. So in order to get that into a mole fraction, I need to divide by 10 to the 6. So this is my equation for sweep through. All I've done is I've plugged in the numbers. 9,000 ppm equates to 0.009 mole fraction, just again by dividing by million. That's what parts per million means. So there's no fancy concentration to grams per meter cubed or anything like that. But now I can calculate and find T. And the answer that I got was T is equal to 2 minutes. And I should also mention in calculating this, I found it helpful to use the book's version of this equation, which you can just rearrange mine and get to this point as well. But this makes it a little bit easier. This is not the exact same. I've taken the liberty here by defining my concentrations a little bit more carefully. The book uses subscripts 2, 1, and 0, which I find a little bit confusing. So it's initial minus inlet on the top and then final minus inlet on the bottom. Where again, be very careful to distinguish between initial and inlet. Don't just call it in like I've been prone to do and then get confused. Okay, let's circle back and talk about what to do about the impure inert. So there's equation 713 in the book deals with this. And I won't show the derivation, but you probably could fairly easily. All we have to do is just amend our equation. So yj minus, the book calls it y oxy, and this is y in the inert, equals y0, and that is the initial, minus y oxy, which again, I'll call it y inert so that I don't get confused. You're perhaps getting confused, which is not good. Let me just do this then. So this is going to be initial. This is final. And then inert is the amount that is in the inert already. So PL over P high to the J power. And I need parentheses there for the avoidance of doubt. So again, this is just plugging and chugging to find what J is. So I'll do that and I'll come back. And the good news here is that my conclusions were unchanged. So when I plugged in the numbers, I got 2.6 for the vacuum purge, which rounds up to 3, which is the same conclusion we got to before when I was assuming pure inert. So before I had 2.4 cycles, now I have 2.6. So slightly more because of the oxygen in the inert, but because I can only have integer number of cycles anyway, it's still the same number. Pressure was the same. It increased from 3.2 to 3.4, but both ways I round up to 4 no matter what anyway. So a good lesson here may be that here it didn't cost me anything. So the inert that had oxygen in it is likely going to be cheaper to purchase than totally pure inert. But it's still going to take me the same number of cycles either way. All right, hope you found those examples interesting, not too confusing to follow. But I'll wrap this video up. I'll see you next time.